Fine, so here we have the first of the videos for the topic 3 of the IB curriculum on heat and energy, and we're going to go through the curriculum in some detail as we go through this. I'm going to be using some of the FET applications and simulations and so forth. So first part, it says state that temperature determines the direction of thermal energy transfer between two objects. I think that's pretty straightforward. Heat travels from a hot to a colder object. There seeks to be this equilibrium of energy, or spreading all the energy, the heat energy out. So we have that transfer. Second part, state the relationship between the Kelvin and the Celsius scales. Now your Kelvin scale starts at absolute zero, which is the lowest temperature that can be attained, and it is at minus 273 degrees Celsius. So we write the scale as this, that T in the Kelvin scale is equal to T in the Celsius scale plus 273. That is your conversion factor. I think it makes sort of sense. I think you should all be able to see the sense of that statement. Notice that we usually use a capital T when we are dealing with Kelvin, and a small t when you're dealing with Celsius. Your Kelvin is your SI unit for temperature, so it's the one that we would want to be using. We use that a lot, and in most of the formulas we would put that in. It's only when we're looking at a change in temperature, because the actual 1 Kelvin, if we change the temperature by 1 Kelvin, or if we change the temperature by 1 degree Celsius, if we have a change in that temperature, these are equivalent. The actual 1 degree and 1 Kelvin is the same amount. So sometimes we won't worry too much whether it's Celsius or Kelvin. When we are looking at a change in temperature, then it won't matter. But generally, always use Kelvin, always convert to Kelvin. Then we have this state that the internal energy of a substance is the total potential energy and random kinetic energy of the molecules. And I'm going to spend a little bit of time talking about this. I firstly want to talk about this random kinetic energy of the molecules, or the atoms, or the particles in a substance. Now, this random kinetic energy determines the temperature. So here we have our definition of temperature. It's a measure of the average random kinetic energy of the particles in a substance. So the temperature gives an indication of how quickly the particles are moving. They can be moving in all different ways. Sometimes when they are fixed, there may be vibrational or rotational, or it may be translational. It may be the particle may be moving from one place to the other. It might vibrate to and fro, or it might be turning. It might be spinning around. These are all forms of motion. They would all contribute to the kinetic energy, and therefore make something feel hotter or colder. So we'll have a look at that. We also look at this potential energy. What does that actually mean? I want to spend a bit of time looking at that now. What does this idea of the potential energy of the molecules? Now, to do this, I would like to use the application. We're going to use this application over here. You can see we are at 20 Kelvin at the moment, so it's pretty cold. That gives an indication, remember, of the average kinetic energy of the particles. So if I heat this up, if I add some heat to this and the temperature goes up, you can see from the simulation that the particles are moving about more. There's more movement in those particles, therefore the kinetic energy is moving. It's reflected in the temperature. As I move it further up, this is oxygen that we're dealing with. As we move it further up, we're going to find that they're going to start breaking apart. They've got enough energy to break the bonds that are holding them together, and so they start moving around in the container. So this is the idea. The 207 degrees, 207 Kelvin, is giving us an indication of how much kinetic energy they've got. But as you could see within that, before they were actually all stuck together, let me just bring that down again. Let me just remove the heat and then bring it down to where we were. What's happening is they're starting to move slower, but they're also starting to join together. The intermolecular bonds are strong enough to hold them together, and as you can see, they're starting to collate, form together. Those intermolecular bonds are strong enough. Now that gives us an indication of the potential energy. It's the bonding energy. And to consider this in a little bit more, I want to use this application over here. We'll use the adjustable attraction. Now this is looking at the bonding, at the bonding energy. And basically what we do is we take, when atoms are separated, now I'm pull this apart completely, when they are separated apart, we are at this position over here, we take it that they are at the zero. So we take when they are far away being zero. But to get them there, you actually have to do work on them. You have to put energy in to actually separate them, to pull them out of what we would call like an energy well there. So when we bring them closer together, when we bring them together like that, and they start to move closer, let me just put this in there, we can see here that this particle is vibrating within the energy well of the other molecule. It has got a certain potential energy. As I pull it out, I actually increase the potential energy. So going back to this one over here, as I increase the energy here, some of the energy is actually being used to break apart, to pull apart. So these particles are not only gaining in kinetic energy, they are also gaining in the potential energy, in that we had to give energy to the particles to break those bonds, to pull apart. And it's a combination of both the kinetic energy and the potential energy that makes up the internal energy of the substance. So the internal energy of the substance is the total potential energy, that's overcoming the bond energy, and the random kinetic energy, that's the movement energy of the particles. Okay, I hope that makes sense. It's a very important concept for it to make sure that you understand. Okay, so moving down here, let's move further down. We have over here explained the macroscopic concepts of temperature, internal energy, and thermal energy. Here we have these aspects of temperature, as it's a measure of hotness or coldness, and gives an indication on a microscopic level of the average kinetic energy of the particles. The internal energy is the total energy that we put in. And we're going to see this a lot when we look at different substances. So, for instance, if we have a beaker and we have got some ice blocks, say some ice blocks, maybe they are at -5 degrees Celsius. As we heat this up, as we put in energy into the substance, that may cause these ice blocks to actually melt, to form water. Now there may be a temperature increase, so there your temperature is increasing, and therefore the average kinetic energy of the particles is increasing. But also what's happening is that the potential energy is changing. So they are these ice blocks may form some water. Now the potential energy is actually increased, and then maybe it will, after a while, it will start bubbling up, and you'll get water bubbling off, and it becomes water vapor. The potential energy also increases, and maybe you'll go up to 0 degrees, and then you'll go up to 100 degrees Celsius. The kinetic energy is increasing. So we're going to be looking at these macroscopic concepts of melting and heating up and boiling and so forth, evaporation in terms of their potential and their kinetic energies. Okay, thank you very much.